This video is about power dissipation in field effect transistors, corresponding to the second part of section 32.6 in the book. Let's take a look at where the power dissipation comes from. Okay, let's start with a fairly simple circuit of just a resistive load and an MFET. So low side switching. When are we going to have power dissipated in the transistor? Well, what we're interested in is power. Instantaneous power is the instantaneous current times the instantaneous voltage. And we're interested in the drain current, and the voltage across the transistor is just the drain voltage because we've got the source here tied to ground. So what we're interested in is this power. Well, there's two basic states for the transistor. When the transistor is off. When the transistor is off, field effect transistors are really good at turning off, and ID is essentially 0. And so power is essentially 0. Now that's not a perfect analysis. If we were looking for a micro power circuit, something that has to run off of battery for years, like a watch, then you start worrying about leakage currents and stuff like that that are very, very tiny, but could matter in micro power systems. When we're looking at power transistors and switching large loads, the leakages are negligible and we can treat them just as 0. When things are on, though, we have a large current. That's what we're doing, why we use power transistors, is to be able to switch large currents. And the voltage is that large current times whatever the on resistance is of our resistor. So the power is the voltage squared, or the current squared, times the on resistance. Okay, so that is one static source of power dissipation. When the transistor is on, we have power dissipation that's current squared times the on resistance. The only way we can keep that small, well, either switching small currents, but the whole point of the power transistor is to switch large currents, keeping our on small. That generally means larger transistors, more expensive transistors, and it also means transistors that take longer time to turn on and off because they have a bigger gate capacitance. But that power, so nothing when it's off, I squared R on when it's on, that is the static power. And about the only ways we have to reducing the static power is either choosing a transistor with a very small on resistance or not having it on very much. You can have something where you only turn it on for a short amount of time, then the power, if it's only on for 10% of the time, the average power is only 10% of this peak power. If that was the only power we have to worry about, it'd be very simple to do the designs we need. But there is another source of power that's often as important. And that's because if we take a look at what's going on with the voltage, when the thing is off, then we're up here at the maximum voltage. And then when we turn it on, we switch and come down, not quite to 0, but to the IDR on. Okay, what happens with the current at the same time? Well, when the transistor was off, the current was 0. Then the current ramps up here until we get up to the maximum drain current. We analyzed basically 0 over here and I squared R on here. But what happens in this transition region as the transistor is turning on, and the same thing happens when the transistor is turning off also. We don't go instantaneously from zero current to full current, or from the high voltage to the low voltage. It takes some time to make that transition. Well, we can make a rough approximation of this with a pretty simple model. We can pretend like these lines here are straight lines, and if we've got a resistive load here, that's actually not a very bad approximation. The current goes up at the same time the voltage goes down. Okay, so what happens to the power? Well, if we've got one that's, say, this is going up as t over, let's give this transition time here a name, capital T, and let's make time 0 just when we start here. So the current going up here is T over capital T times whatever the maximum current is in this transition region from 0 to T. So that's current as a function of time. Voltage as a function of time, well, it's going to be Vmax, whatever we started with the beginning here, times 1 minus little t time over how long that time interval is. So the power is going to be, notice I lied here just a little bit because this one goes down to 0, and there's actually, it doesn't quite go down to 0. You can fuss with the equation just a little bit to fix that, but I'm going to take the simplification that the static power here is small or the error from using the 0 rather than IDR on is small. So we're going to get Imax times Vmax times T over T minus T squared over T. T over T quantity squared. So the power in the spike is corresponding to the max power we would get if we had the full current and the full voltage at the same time, but it's got this quadratic in here, so it goes something like that, where the peak here would be at time being a half, so that's about 1/4 of Imax Vmax. If we want to figure out how much energy is, I mean, this is a kind of complicated power curve. We want to figure out how much energy was in this switching event, which is sometimes referred to as the switching energy. We just have to integrate this power from 0 to t, and that's fairly simple calculus. I'm not going to bother writing it here, but it comes out to 1/6 Imax Vmax times the duration. So that's the total switching energy of one of these turning on events. Notice that as we make this transition faster, reducing this time for the transition, the power dissipated, or the energy dissipated, is reduced. The shape of the curve here is not really too critical. If you get something that's not exactly a parabola, but it's, goes up to about 1/4 and comes back down again, you're going to get an integral that comes out close to this. So even though this was a very crude approximation, it's not a bad value. Now we're going to have two of these events, and they may actually have different times because the transistor may turn on, turn off at different speeds, but approximately this amount for each event. And so if we're going to do this thing many times a second, we're going to be turning the thing on, turning the thing off a lot, then the power that's dissipated in switching is how many of these events are there per second times this energy in each one of the events. And if there are a lot of events per second, this power here can be quite substantial because Imax times Vmax is very much larger than the static power here, the ID squared R on, because here our voltage was quite small. But here we're looking at the maximum voltage times the maximum current. So we have to make sure that this time, the switching time, is a very small fraction of the total period of how often we're switching it. So we want to switch either very rarely or very quickly, or ideally both. Switch as rarely as you can and as fast as you can each time you do switch to minimize the power that's lost in these switching events. Okay, so if you have to do a calculation for how hot a transistor is going to get, what you need to look at is two things. How much static power is there from the thing being on, and then you have to look at the duty cycle, what fraction of the time is the transistor on, and how often do you switch it, how frequently do you switch it, and how fast can you get that switching to go. And multiplying how fast, multiplying the switching energy for each transition times the number of transitions there are per second would give you the switching power. You have to add both the switching power and the static power together to get the total power that's dissipated by the transistor. And I think that's pretty much all you need to know in order to be able to calculate the power that's dissipated in a field effect transistor.